In this lecture session, I am going to present the topic on switching characteristics of the thyristor, through which we can identify how much time is required during turn on as well as during turn off. Moreover, overall turn on process and turn off process of thyristor. First, I am talking about the turn on process. The turn on time can be divided into three categories. If we consider the total time on time, that is defined by suppose T on, which will be equal to delay time Td plus rise time Tr plus spread time Tp. And to identify Td, Tr and Tp, first we should recall the basic structure of Scr. I think it's known by everyone. That is, Scr has 4 layers like this: P, N, P, N. Gate is connected over here, that is gate terminal, and the cathode is connected, that is K, and the anode is connected to the upper layer P, that is A. And the 3 junctions, that is J1, J2 and this is J3. Suppose thyristor initially is in forward biasing mode, means we can say anode is more positive with respect to cathode, as well as we are giving the gate pulse across gate. That means suppose gate is positive with respect to cathode. When we applied the gate pulse across gate, then the gate currents begins to flow from gate to cathode in this way. As the gate current begins to flow from gate to cathode, gate current has non-uniform distribution due to P layer. The value is maximum near the gate and decreases rapidly from the gate increases. At this situation, when the anode current starts flowing in this way, and it covers the narrow region near the gate where the gate current density is highest. As the gate current density is highest near the lower N region and P region, that is why there is no free space to easily conduct the anode current, and due to which there is a concept of delay time. This is called Td or delay time. To be very detailed, if we consider this is the cross-sectional view of the of the cathode, then the anode current is flowing through the cathode is very narrow region. Just I am drawing this part by a point. In this case, as the gate current rises 0.1 Ig from its initial value, that means when it reaches 90% of its initial value, then we can say the anode voltage falls from VA to 0.9 VA, means the voltage falls from its initial value to 90% of the initial value, and the time during which the anode current rises from its forward leakage current to 10% of the original value. So this is all about for the delay time, which is defined by Td. Now the question is Tr or spread time. In this case, the anode current starts spreading from narrow conduction region near gate, but this time is not able to spread over the entire cross section of the cathode. That means we can say in this particular case, then the anode current starts spreading similar to this manner. Mean it was first defined by a point, now it starts spreading in this way. Okay? But it is not able to cover the entire cross section of the cathode. That is why we cannot say the anode current starts conducting easily. That is why the duration of this time is called rise time. Additionally, we must say in this case, time taken by anode current to rise from its 0.1 IA to 0.9 A, that means we can say the anode current rises from 10% of the original current to the 90% of its initial value. As well as we can say on the other word, that is time taken by forward blocking voltage falls from its initial value of 90% to 10% VA. That means the anode voltage falls from 0.9 VA to 0.9 VA to 0.1 VA. Now the question for spread time. In this case, the spreading velocity of the gate current is too much high. That is why the anode current spreaded throughout the entire cross section of the cathode. So we can say in this case, if we consider this is the cross section of the cathode, then the anode current is spreaded entire section of the cathode. So due to which it has taken some time, this is really defined by TP or spread time. And this spreading interval depends on cathode area as well as the gate structure. So this is a basic concept of delay time TD, rise time TR, and the spread time TP. Now the question is, during turn off, what happened? As we all know, the thyristor can be turned off by reducing its anode current below holding current. Okay, that is why just like a turn-on process, it requires a few amount of time during turn-off process, which is defined by TQ, which can be defined by TQ or total time turn-off time, that should be equal to TRR, or which is called reverse recovery time, plus TGR, which is called gate recovery time or recombination time. But the question is, in which way we can reduce the anode current below holding current? So again, let me draw the basic structure of the SCR that is known by everyone. It has four layers, PN, 3 junctions, J1, J2 and J3, and 3 terminals, anode, cathode and gate. Initially, this device was in conducting state. That is why we assume the anode was more positive with respect to cathode, and additionally we had given the gate voltage across gate. That means gate is more positive with respect to cathode. But now we are trying to switch off this device. That means we are trying to reduce the anode current which was established during turn-on process below holding current. How can it possible? So to consider the holding current, the anode current which will reach below holding current, that is why suppose we are adding some negative biasing over here. That means negative biasing means we consider the switch is under on state. Right now we are trying to off the switch, then just we have applied the negative biasing additionally across the device. So we can say the cathode is negative biased with respect to anode, means we can say we are applying an additional negative biasing like this. Just you can assume in this way. I don't know it is the right approach or wrong approach, but you can think in this way. Okay, that means we can say when the cathode is positive with respect to anode, then what happen? As the cathode is positive with respect to anode, then for the lower n region in which the majority carriers are electron that should be attracted by this positive cathode terminal, and in case of the upper p region where the majority carriers are holes that should be attracted by the negative anode terminal. Okay, that means few amount of charges that will be sweeping out from upper p region as well as lower n region in this way. Once the 60% charges are sweeping out from upper p and lower n region, then there is a question of the tendency of formation of the depletion layer across junction J1 and the junction J3 as the charges are removed from the upper p and lower n region. That means the charge density is reduced. That is why junction J1 and J3 try to recover as the depletion layer will form across the junction J1 and J3. Okay. Now think about it. Once the junction J1 and J3 is reformed, that means then the current cannot flow easily from anode to cathode as it was forward biased before. That means now the actual anode current, which is responsible for the majority carrier movement, that can be opposed by the depletion layer across junction J1 and the junction J3. Okay? And the duration of this particular phenomena, that is defined by TRR or recovery time, as we are giving the reverse biasing voltage across the device. That is why somehow it can be said reverse recovery time or defined by TRR. That means we can say during this interval the junction J1 and the junction J3 both are reformed, means the depletion layer has formed. But the trap charges which has moved from suppose P to N layer or N to P layer, they are actually called some trap charges that is still moving in nature across the junction J2. That means internally there is a tendency of the current flow. That is why we cannot say the thyristor is off. So the thyristor can be completely off when the junction J2 will be reformed. Okay? That can be possible by adding this reverse biasing still. That means what? That means it will give some force the internal charges or the trap charges which was in moving condition across the junction J2. Then this additional reverse biasing force, then the hole and electron try to recombine by each other and it will form a immobile charges. That means then the carrier charges or which is responsible to making the anode current, the density of the charges will be removed as few of the charges are recombined and they form a immobile ion. That is why the free electron and the free holes are reduced. So we can say now the junction J2 has reformed or the depletion layer again regained across the junction J2. So for this phenomena, the requirement of time that is defined by TGR or gate recovery, as the P layer is connected to the gate, that is why junction J2 has reformed, and for the interval of reformation this junction J2, this is well defined by the gate recovery time and defined by TGR. So this is all about for the time duration during turn off and which is defined by TQ or turn off time. So this is the all description I have discussed for turn on time and turn off time. So let we go for the basic switching characteristics for any SCR. So, this is the pictorial representation for overall switching characteristics of the thyristor during turn on and turn off, in which the first one, that is defined by the gate voltage, okay, that is Vg, and this is for anode voltage as well as gate current, that is why it stands for Va and Ig. This axis for anode current Ia, and this is actually for the power loss axis. This is a total time taken during turn on, which is defined by T or T on. Normally, for a reliable thyristor, the requirement of this turn on, that is 124 microsecond, and which is divided into three parts, just I discussed before, that is TD, delay time, TR, rise time, and TP, that is spread time. And we all know why the delay time and rise time and spread time has there. Due to the current movement, anode current movement for the cross-sectional area of the cathode, and due to uneven distribution of the gate, the anode current initially starts moving in a narrow region of the cathode, that is defined by TD, and the spread time when the anode current starts spreading to the cathode cross-section, but it is not able to cover the entire cross-sectional area, that is why the duration of the time is supposed TR. And when TP means the spread time, means when the anode current is entirely spreaded over the total cross-sectional area of the cathode. So this is actually called the total time duration during turn on, defined by TQ. In this part, that is the turn off time duration, and which can be splitted by the two duration, that is TRR, that is reverse recovery time, in which the junction J1 and J3 has reformed, okay, and maintaining the reverse biasing across the switch, and this is gate recovery time defined by TGR, in which the junction J2 has reformed due to recombination of the free charges, and it will neutralize and form a immobile charges or immobile particle, and the requirement of the time, that is called actually gate recovery time, and which is normally defined by TGR, as well as we can say it's a recombination time, as the charges are recombined by each other to form the neutral ion, okay, or immobile charges. So total time, that is TRR plus TGR, that is actually called turn off time, which is defined by TQ. Okay, fine. Now recall the operation. Suppose first we have applied the gate pulse over here. When the gate starts spreading, we know it is very clear to us now. When we are applied the gate voltage across gate, then the gate current starts spreading, or it starts rises. Okay, when the gate current is spreaded over the entire P region, then the anode current starts moving freely, as there is a huge free space. Okay, now this is a gate pulse. One thing, keep it in your mind, once the thyristor starts conducting, once the anode current starts flowing throughout the junctions and it reaches the latching current IL, then we can remove the gate from the terminal. Still, the device will be under conduction period, or device becomes in on state. Then the gate will not influence the conduction time or conduction process. Okay, that means only the gate is required during initialization of the turn on process. And keep it in your mind, once the thyristor starts conducting, then we can remove the gate from the thyristor. It will not affect the conduction. Okay, That is why we cannot draw the signal throughout the entire time axis. Okay, we have stopped here. That is only for the turn on process applicable. Okay. Next is that is VA as well as gate. So considering all the before discussion, we can say when the gate current rises up to 90% and we applied the forward biasing across the anode, that is VA, then still the device is under blocking state. That is why no current is increasing, anode current is not increased. That means this is a small amount of anode current which is called leakage current due to presence of the reverse bias junction J2. Once the thyristor will be turned on, then the voltage will fall as well as the current rises. Okay, that means after when the gate current rises 90% of its initial value to 100%, this particular region, then the anode current starts falling. Once the anode current starts flowing, then the anode voltage starts falling as well as the anode current starts increasing. That means right now we can say the turn on process initiating. Okay. After that, what happened? When the gate is in a constant magnitude 100% of its initial value, then automatically at the gate current spreaded over the entire P region that is directly connected to the P region, then the anode voltage starts falling to a particular value and the anode current rises up to a particular value. That means we can say in this particular region or spreading region, then the current try to increase sharply and the voltage is falls and decreases sharply, and it will reach up to the 10% of its initial value and the current rises up to 90% of its initial value. That means almost a device will be in under conduction mode. After that, see in the spreading region, see the anode current rises from the 90% to the rated value. That means we can say in this particular region the device starts conducting, and once the device starts conducting, obviously anode voltage should fall. As that means the anode voltage is falling from its 10% to the on-state voltage drop, not exactly to zero. As we know, as per the basic construction, it has the 4 layers and 3 junctions. That is why there must have some ohmic drop, due to which there is a small amount of the voltage drop can be occurred during the whole on process and when the device starts conducting throughout. That is why this is defined by on-state voltage drop, and this is around 1 to 1.5 volt. Okay, that means we can say this region is actually the switch becomes on. That means without any disturbance, the anode current starts flowing throughout the device and the voltage, that is minimum voltage drop, occur due to 4 layers and 3 junctions. Okay. Suppose we are trying, so that is why this is for actually conduction period. Okay. Now suppose we are trying to switch off this device. We know the device can be switched off when the anode current falls below holding current. So suppose we are trying to fall the anode current from this point below a certain amount. So think about this region from this one to this one. Then what happened? The device still is under working state, as because the internal charges are still in moving condition, and it is known by everyone that the current flowing, the direction of the current, that should be equal to the direction of the hole and the opposite direction of the electron. That means in case of the PN-PN layer, when the holes and the electrons still in moving condition, that means the internally current has moved. That is why we can say up to this region, when we are trying to decrease this anode current to a value of suppose 0, still at this point the device is under working state. But the application of the reverse biasing during turn-on process, the anode current again fall from 0 to a lower value. That means almost is a minus current or negative current starts flowing. Once the negative current starts flowing, when it reaches just the time of T2, then what happens? Then the 60% charges that will be sweeping out from the upper P and lower N region. Okay, that means from this point, which is connected to this axis and which is defined by T2, then the turn-off process initiating. Okay, what happened between this duration T2 to T3? That means when the 60% charges are sweeping out from upper P and lower N region, just I discussed before, that means then automatically the depletion layer has formed across junction J1 and J3. That means original anode current is opposed by these two depletion layer of junction. Okay, that is why once the anode current is opposed due to these two depletion layer across junction J1 and J3, then automatically the reverse voltage has appeared across the thyristor. So this is the reverse voltage appeared across thyristor. Okay, up to the time axis T3. That means up to this point, as the junction J1 and J3 has regained its depletion layer, that is why this is called recovery time. Just I discussed before. Okay. Similarly, what happened? At the point T3, still the few amount of trapped charges which still is moving condition internally across the junction J2. That means junction J2 is not yet formed. If the junction is not yet reformed, then we cannot say the device is under off state. That is why still we should maintain that reverse biasing across cathode to anode. That is why this time duration, I am talking about T3 to T4, that means then due to recombination technique, the junction J2 regain its depletion layer. That is why this time is called recombination time. As this is connected to the gate terminal, that is why we can say this is gate recovery time also. Okay, so we can say when the graph reaches at the point of T4, then we can say the anode current is right now is 0. Okay, and the anode voltage is 0. That means we can say up to this point, this at which the switch will be off. Okay, so this is actually defined by TQ or the off time TQ. But actually we are using this kind of switch or SCR for some power device or some power circuits. That means somehow the SCR can be connected to other equipments or other components like inductor, like capacitor, like resistor, or so many other components can be there. That means what? That means if we should properly turn off this switch, that means all the charges which has stored in the other equipment or the other components, that should be removed first. Then we can say the device will be in off state. That is why it will take more time. So the graph will be extended up to this point. Again, this graph will be extended up to this point at the point of T5. So this is called actually the actual time duration in case of application purpose or in power circuit. Okay, and total time taken during this one, that is defined by suppose TC. This TC always greater than TQ unless we cannot say the reliable turnover process had done. Because of if we cannot reach up to the point TC, suppose assume the switch has been turned off during suppose TQ. Suppose again we are trying to switch on the device, then the breakover voltage can be differ. It can switch on again with a lower breakover voltage, and due to which few switches can be short-circuited. That is not required. That is why to maintain the proper turn-off process or reliable turn-off, always try to maintain the time up to TC or total turn-off time. And this total process is called commutation. Okay? That means turn-off process can be termed by commutation, as it is well defined by here. During initiating of the turn-on process, when the anode current falls below holding current with a dIdt slope or rate of change of current with respect to time axis, that is called commutation. Okay? So, to proper commutation, try to maintain the turn-off time up to TC. Fine. So, from my aforesaid discussion, the total description is given over here. This is the switching characteristics during turn-on process, and this process is for turn-off process. Here, the time has mentioned, that is delay time, at this instant at which the gate current rises 0.9 Ig to the instant where the anode current rises up to 0.1 Ia, the time during which the anode voltage falls from VA to 0.9 VA, and the time during which the anode current rises from its forward leakage current to 0.1 Ia. And it will cover a very narrow region across the gate. That is why we can say thyristor is initially in forward biasing mode, as well as the anode voltage and the anode current is small when turn-on process starts. Then anode current gate rises and fall anode cathode voltage as the gate current begins to flow from its gate to cathode, and the gate current has non-uniform distribution due to P layer, and the value is maximum near the gate and decreases rapidly from the gate increases. Okay? And the anode current falls in the narrow region near the gate, then gate current density is highest, where the gate current density is highest. So, TD can decreases applying the proper gate current Ig and more forward voltage. Okay? And for TR, or that is called the rise time taken by anode current to rise from 0.Ia to 0.9 Ia time, and the time taken by forward blocking voltage falls from 0.9 VA to 0.1 VA. In this interval, what happened? The anode current starts spreading from narrow conduction region near gate, but the time is not enough to spread over the entire cross section of the cathode. In this period, turn-on loss is maximum at the voltage and current both are in a big value. Okay? So, let me discuss it once. Go to the previous slide. See, in this rise time, as the anode current is maximum as well as the anode voltage is maximum, that means power means voltage into current. That is why the graph is taking this kind of shape where the power loss is maximum. So that means during on time, the power loss is maximum across the time TR or rise time. Now TP means spread time. Time taken by anode current rises from 0.9 Ia to Ia, or time taken by forward blocking voltage falls from 0.1 Ia to on-state initial value conduction spreads over the entire across the section of the cathode. So, in spreading interval depends on the cathode area as well as gate structure. So, total on time depends upon the anode current, parameters and gate signal waveform. Higher magnitude of the gate current, lesser turn on time. If gate current is high with respect to required gate current, thyristor is said to be hard fired or overdriven. Once the thyristor on, gate losses control. Then SCR can be turned off by reducing anode current below holding current. The dynamic process of turn off, that is conduction state to forward blocking state, is called commutation technique. Now, switching characteristics during turn off. As I mentioned earlier, the total time of time TQ, that is defined by recovery time TRR and recombination time TGR. So TQ is the time between the instant anode current becomes zero and SCR regain forward blocking capacity. Before T1, already forward voltage applied to SCR and anode current reduced to zero, which with dIdt slope, but not to holding current. SCR still favorable for conduction due to movement of electrons and holes in the 4 layers. After T1, reversal of anode current due to minority carrier movement as stored in the 4 layers, and few amount of charges, that means sweeping out holes from upper p layer and electrons from bottom n layer. So removes extra carriers from the junctions J1 and J3. At the point T2, when 60% of the stored charges are removed from upper P and lower N region, then junction J1 and J3 has reformed. Reverse current starts decaying fast at the beginning but gradually thereafter. Fast decaying because reversal bias across junction SCR. Surge appears. SCR can be damaged permanently. To avoid it, normally we are using RC circuit. At the point T3, reverse current flows to nearly zero. Junction J1 and J3 recovered. So it is called reverse recovery current or TRR or reverse recovery time. After T3, J3 still has trapped charges, cannot flow through the external circuit. Trapped charges must decay only by recombination. Recombination possible due to maintain the reverse voltage across SCR. Recombination time T3 to T4 is called gate recovery time. That is why defined by TGR. J2 recovered and forward blocking state can be reapplicable. That means we can set a total time defined by TQ for turn off. This TQ applicable to individual SCR separately. In practice, SCR is a part of power circuit, so turn off time maintained by power circuit TC. For reliable commutation technique, TC must be greater than TQ unless otherwise the device may turn on at any unwanted instant or undesired instant, and this is called commutation failure. So this is the all description has given here from the above switching characteristics. Okay, so thank you.